Welcome to the lecture 4.2. Today we're going to discuss about the expected value. We're going to review this a little bit. Then we're going to discuss about the variance. This is another measurement of random variables, which is different from the expected value. We'll try to understand how we can calculate the variances. And also we're going to discuss about the binomial variables, which is really important. So we couldn't do the Bernoulli binomial variables with other groups, so I hope that we will be able to do this with you. So you should help me. So we define the expected value as the weighted average, and we're going to calculate this technically like this. So the meaning of the expected value is simply the average. But of course, if your categories have the different weights, then you're going to find the average of these categories differently. Okay? So I just gave you an example of the expected value. You can do this. So the number of the students who are coming to the lecture is a random variable. If you calculate the expected value of this random variable, it is going to tell you how many students we should expect to come to this lecture, okay? Or for example, as some artist is doing his concerts, okay? And he can calculate, so the number of the people who are going to buy his tickets is also the random variable. So before he starts doing the concert, depending on, so by making the analysis of all of his concerts, previous concerts, he can expect how many tickets are going to be sold. Okay, so this is the meaning of the expected value. So technically, we are going to calculate this by just multiplying every output to its probability, okay? So later on in the notations, I'm just going to leave this indices in the summation because it is somehow clear that it has those indices, and I'm going to write this as x times to the p of x, okay? But whenever I write this, you should understand this x is the variable, is not a constant, okay? So I'm just going to leave this. So this notation, by the way, is called the Einstein's notation because he used to use the tensors, like the multidimensional matrices with lots of indices. So it took a lot of time to write down all of these indices, so he decided, okay, so I will leave this and you should understand this without the indices. Okay, so we're going to do the similar thing. Let's do a small example. So let's say you go to Las Vegas next summer and you would like to play one of these two games in a casino. So one is called the number 7 roulette. The second one is plus line and the dice game of craps. So in the first game, if you bet $5 in number 7 roulette in the first game, so probability that you lose this $5 is 37 over 38, and the probability that you will win the prize, $180, is equal to the 1 over 38. So essentially your gain, net gain, is going to be 175 because you spend $5 to play this. So if you play this game, how much gain you should expect? So in order to do this, we're going to make the table. So here we're going to write down the random variable, right? And its probabilities, okay? So it's a random variable, right? So you're playing this game, and before the game, you don't know whether you're going to win or lose. But there are two possibilities. Either you're going to win and your gain is going to be $175. Either you're going to lose and your gain is going to be minus $5. And the probabilities of these two outputs are given like this. So in order to calculate the expected value, we're going to multiply every output to its corresponding probability, and then we're going to add this. So this output is going to be multiplied to this probability, this output is going to be multiplied to this probability, and then we just need to sum this, and we're going to get this result, minus 0.26 cents, okay, or $0.26. It means that if you play this game, you should expect that you're going to lose 26 cents every time, okay? So it doesn't make sense when you're going to play this game only once. It makes sense when you're going to play this game in the long range. So in converse, in the second game, probability that you're going to, so you can earn some money, so $10, and the probability of earning $10 or gaining $5, okay, because you spend $5 to play, is equal to the 244 to the 495, and the probability of losing this game is 251 to the 495. And we can calculate the expected value in the same way, and you can see here that the expected value is only minus 8 cents. So even though the gain for the first game, so you have the larger payoff for the first game, In the long range, the second game is more profitable because you're losing less amount of the money in a single game. Okay, so we again use the expected value not to predict the results of a single game. So you need to use the expected value in order to make the predictions in the long run. So, well, it basically tells you that, hey, if you play this game, the second game, in the long range, for every game you're going to lose 8 cents. And if you play the first game, in the long range, you're going to lose 26 cents in every game. Okay? So this is the meaning of the expected value. So we better try to understand the meaning of the expected value rather than just the formula, because the formula is very much straightforward. Cool. So let's say I've got two random variables, x and y, and I would like to calculate the expected value. Could you please look to this table and tell me what is the expected value of the x and what is the expected value of the y? The expected value of the x is 0, expected value of the y is also 0, right? How do you know this? By just making the calculations, right? Oh, by the way, do you know that expected value is simply the scalar product of the two vectors? So essentially, here you've got one vector x with the two outputs or two entries, -1 and 1, and you've got another vector p with again like a 2 by 1 vector, 0.5 and 0.5. And if you multiply the scalar product x to the p, or sometimes we denote this as a x dot to the p, you're going to have 0. It is a scalar product of the two vectors, okay? So technically, you should understand the expected value like this, and this is essentially how you can implement the expected value in the computers, okay? So in the computers, you are not going to write down the loops, for example. You can basically define the two vectors, and you can multiply these two vectors as a scalar product in order to get the expected value. Okay, so you see, so the expected value of the x is equal to the 0, the expected value of the y is also equal to the 0, and if I would like to compare these two values, two variables, using the expected value, it is going to be very much difficult. Okay, the expected value for both of the cases, it is the same, but it is clear that these two variables are different, right? So let us sketch these two variables. So if I put these two variables, so essentially, for example, the x, so it is going to be here, the y-axis is going to be in the probability. So the probability is 0.5. It is the same for both of the values. And the probability for, and the second variable is going to be here, okay? So the first variable is -1 and 1. The second variable is -100 and 100, right? Even though the expected, and the average is going to be like this. So what is the average distance between them, right? Average distance is here, right? It is clear because they are symmetric over this line, okay? And it appears the expected value is not a good tool, for example, to compare these two sets or two variables, because it is giving the same result, even though they are completely different, okay? So what I would like to use in order to compare them is the variance. So how much the spreadity of these two variables, okay? So how much these variables are spread, okay? So this is what is called the variance. So the variance is the measurement of the spread of the variables or the spread of the data sets, okay? So well, when you look to the variables, you should look to them as a data sets, for example. Because this is the random variable, you can make the experiment many times and you can get lots of values, right? But for the first variable, you're always going to have the values here. And for the second variable, you're always going to have the variables there and here, okay? So here is the variance, and it is clear that the variance for the second variable is much more than the variance for the first variable. And this is going to be the second measurement, how we can compare these two variables. So now we need to figure out how to measure this variable, variance. And you should help me. So yesterday in a previous group, they came up with an idea how to calculate this technically. And I hope that you will be able to do this as well. So do you have any ideas how we can measure the variance? So let's say I gave you two sets, and you need to tell me the formula. You need to figure out the formula, how we can measure the variance without Googling it.
Subtraction.
Subtract the distance between the points, or what do you mean?
Between the variables, for example. 100 minus 100.
Okay, 100 minus 100?
Minus.
Minus 100? It's going to be 200, right? And for the second one, it's going to be 2, right? So we can measure, for example, the variance by subtracting the distances between 2 points. But what if you have lots of points? For example, you have this amount of the points.
The highest value and the lowest.
Highest value and the lowest value.
Yeah.
Okay? For example, for this red set, you've got this 5 points and one more point out of there in million. There, millions. Okay? And then, of course, that here. So in this case, the variance for the red set is going to be bigger than the variance for the blue set. Right? Is it clear? Yes? So this measurement of the variance is basically called the range. Okay? So the idea which you told. So it is one way. Okay? So yeah, it's correct. So we can take the difference between the highest value and the lowest value. But the problem is it is very sensitive to so-called outliers. The outliers which are far away from the others. Okay? So in this case, it is clear that the blue set has a lower variance, but by your calculations, the red set is going to give you the higher variance because of this outlier. Okay? In general, if your set doesn't have the outlier, it's a good tool to measure the variance. Okay? So again, taking the difference is a good way, okay? But we need to improve this. So, but probably taking the differences between the points is not a good idea because, like, if all of your points in one side, for example, then again, so the distance is not a good tool. But I like the example was a tool. So I like the idea was the distances. Sorry. Do you have any ideas how to improve this?
Maybe we should somehow group the majority of the dots.
Okay, there.
Then find the distance.
Distance between what? Between the points?
The lowest and the highest.
Oh, between.
We just need to somehow,
Okay.
took 90% of the distance.
Okay, which distances we need to find?
We should just add all the x's variables without multiplying their respective probabilities and just divide it by the number.
But the probability is frequency, you know what I mean? So the higher the probability means that more points you're going to have there.
We should consider probability also.
Of course, because like if you have like 100 points here, because if the probability is higher, it means that more points will be here. And if this point has the lower probability, it means that it's going to be only 1 point here. Okay? Obviously, the probability is important as well. So the probability is the same as the frequency. You should know this because I think we did this example, right? When we talk about how to calculate the probabilities using the tables of the polygraph test with the positive and negative values. Do you remember? We used the frequencies, right? The frequency and the probability is interchangeable things. Okay, so my idea would be like this. So we are going to find the distances between all of the points and the mean. So we first of all are going to find the mean. So in this case, it is going to be here. Then we're going to find the distances between all of the points and the mean. And then we're going to find the average of those distances. The variance is going to be measured by finding the average of all of the distances from the mean. Okay? So it is the same as your grouping, right? So more points means that the mean is going to be there somewhere. Okay? Then we're going to find the distances between all of the points and the mean. Okay, for example, you've got lots of points here. Okay, it means that the mean is going to be somewhere here, somewhere here. And then we're going to find the distances. This distance, this. And then we're going to find the average of all of these distances. Okay, and this is going to be the variance. Okay, so now we need to implement this. Okay, so now we need to figure out the formula, and you need to help me to do this. Okay? Well, we are going to use this function, e of x. So e is the function. So you are the software engineers, yet like you need to understand me, right? So when you apply this e to the x here, it is going to give you the average of the vector, average of the vector x. Okay? So here you need to look to this x, not as the variable or not as the one number. You need to look to this x as the array. Okay, so you've got an array, you call this as the x. If you just apply this function e, it is simply going to give you the average of this x. Okay, if you have another array, for example y, if you just apply this e to the y, it is going to give you the average of the y. Okay, in general we can find so by the way, how we can find the distances between the points and the mean. So how do you find the distances, by the way? If I give you 2 points, A and B, on the line, how do you find the distance? Take the difference? Yes? But the difference can be negative. Square, okay. So we take the difference between the 2 points and square this, and it is going to tell us the distance, okay? So it is better than the absolute value, okay? Because square is a better function, okay? It's differentiable, it's continuous, it's more nicer to work with. So we find the distance between the points by taking the difference. So this is going to be the distance between points and the mean, okay? We take the difference and square this. Here, x is an array, okay? It's not a variable, is it an array? So let's assume that here, when I denote the capital X, so you see, so in some slides, I use the small x. In some slides, I have a capital X. I'm not doing this at random, okay? There is a meaning, okay? So when I write down the capital X, it means that this is an array. This is a variable. In your language, this is an array. When I write down the small x, it means it is a specific value of that array. xi, x1, x0, whatever. Some element of that array. So there is a meaning between the capital X, there's a difference between the capital X and the small x. So here, when I say that the capital X for the x, so it would mean some array. For example, 1, 2, 3, 4, and 5. So when I just apply the E of x, it is simply going to give me the number. What is this number? Can you tell me what is the E of x here? Yeah. It's a mu. What is the value of this mu? 3. Okay. How do you know this? It's an average, right? You sum these 5 numbers and divide this to the 5. 15 over 5, it's going to be 3. Okay? So do you understand functionality of this E? So if you've got an array, if you just apply the array, it is going to give you the average. Okay? So here, when I write down this expression, it is not just one value. It is again the array. So have you worked with some, like a vector programming language, like in MATLAB or R or something like this? So it is maybe in C++, maybe? I don't know. I'm not sure about whether you can do this in C++. But in MATLAB, if you have an array, if you just subtract one constant from the array and square this, it is going to give you another array. And it's super easy to do. So actually here, this is going to be also an array, and it has 5 values. Can you tell me the values of this array? 4, 1, 0, 1, and 4. Those are the values of this array. So we found all of the distances between all of the points and the mean. Okay? How to find the average of this? Formula-wise. How I should put the formula here? How the variance, how the average of this 5 values, how the average of this array can be found. Do you remember how I found the average of that array x? By just applying the E. I just applied the E to the array, it gave me the average. I just applied the E to the Y, it gave me average. If I would apply the E to this array, it gives me the average, okay? And that's going to be the formula for the variance. So the variance is going to be defined as an average distance between all of the points, okay? So sometimes this formula is given, but the meaning of the variance is super clear, actually. So you're finding all of the distances from the mean. So this is the distance, the measurement of the distance. And then you're finding the average. Cool. Now we need to learn how to calculate this for the probabilities, okay, for the variables. Fortunately, we know how to calculate the expected value of the functions of the random variables. I hope that you watched the lectures from the previous one. So in the previous lecture, we in particular talk about, hey, if you've got E of x, you're going to calculate this by multiplying x as a p of x. Okay? But at the same time, if you need to calculate the expected value of the x in the square or some function or any function, for example, E of sine of x of your random variable. And if you know the math function for your random variable, what you do is essentially you're going to sum x squared to the p of x. Or you make the sum of the sine of x to the p of x. So this is how you're going to apply the expected value with respect to the random variables. So this p of x is always the same. You just need to evaluate the values of your random variable for this new function, Okay, and multiply this to the p of x. So the same as here. So we can do the same thing here. So here's a table which you need to fill out. So here, your random variable x is an output when you roll a die. It has the probabilities, the same probabilities, like a 1 over 6. Then you just need to calculate the expected value, the x minus p of e of x in the square, then the variance. Okay? So, I mean, essentially, this is how you calculate the variance. Did someone calculate it? 2.91, right? So if you calculate the variance, you're going to get the 2.91, okay? So it usually takes a lot of efforts to calculate the variance using this way, but fortunately for us, there is an easier way. And we are going to do this now, an easier way, okay? So we can calculate the variance using this formula by calculating the expected value of the x in the square minus the expected value of the x in the square. And before we use this formula, we are going to derive this. First of all, we're going to prove this. So let's try to do this. So the expected value of the x is equal to the summation of x times the p of x. And we also denote this as the mu. It's a constant. So what is the expected value of the x minus mu in the square? It is the summation of x minus mu in the square times the p of x, analogously what we did for the expected value of the x. And I'm going to open the brackets. It is going to be x in the square minus 2 mu x plus the mu in the square times the p of x. So I'm going to apply the summation for each of the terms in the summation. That is going to be x squared times the p of x minus summation of 2 mu x times the p of x plus the summation of the mu in the square times the p of x. So if the summation of the x to the p of x is the e of x, what is the summation of the x squared times the p of x? E of what? X squared. Okay. Minus. So the 2 mu does not depend on the sum, right? On the indices. So that is why I can take this out. 2 mu, the summation of the x times the p of x. Plus, I can take out the mu squared as well from the summation because it is a constant. It doesn't depend on that. So if, so we know that x times the p of x is the e of x, or it is simply the mu. What is the summation of all of the probabilities? 1. So this is equal to the 1, summation of all of the probabilities. So what we have here is e of x in the square minus 2 mu times the mu, because this is mu, plus the mu in the square. And this is equal to e of x in the square minus e of x squared. Okay, because you've got minus 2 mu squared plus mu squared, which is minus mu squared. And we know that the mu squared is the e of x in the square. So this is a simplified version of this formula for the variance. And most of the time, it is easier to use this formula rather than the definition of the variance. Cool. So we are going to do an exercise. So let x is the number of the heads when you toss a coin 3 times. Find the variance of the x. You toss the coin 3 times and you count the number of the heads you got. Could you please tell me, is it a random variable? For example, I toss the coin 3 times, I've got 1 heads only. I toss the coin 3 times, I've got 2 heads only. Is it a random variable? Yes, right? What kind of values it can take? So how many heads you can get when you toss the coin 3 times? 3? 1, 2, 3. 1, 2, 3? 0. Okay. You can take no heads at all, only 1 or 2 or 3 heads. So what is the probability of getting 0 heads? Well, in order to calculate those probabilities, we need to basically simulate the scenarios, right? So what kind of scenario you should obtain in order to get no heads? T, right? So you should get, so the probability that x is equal to the 0 means that you need to find the probability of this scenario. You've got tails, tails, tails. 3 times. So according to the multiplication rule, it is going to be probability of the tails times the probability of the tails times the probability of the tails, which is 1 over 2 multiplied to itself 3 times. It is going to be equal to the 1 over 8. So what is the probability that x is equal to the 1? So it is either you get tails, heads, tails, or you get heads, tails, tails, or you get tails, tails, heads, right? There are 3 scenarios when you are going to obtain only one heads. Either in the first case, tails, heads, tails, or heads, tails, tails, or tails, tails, heads. So the probabilities of each of them is 1 over 8, right? Because we know that the probability of getting tails or head are the same, 1 over 2. If you just multiply 1 over 2 to itself 3 times, you're going to get 1 over 8. That is going to be equal to the 3 over 8. Well, what is the probability that x is equal to the 2? Again, there are 3 cases, right? So the 2 heads. It is like a head, heads, tails, or heads, tails, heads, or tails, head, head. And this is also going to be equal to the 3 over 8, and the probability of x is equal to the 3 is equal to only one scenario. You can get this heads, heads, and heads. So this is going to be equal to the 1 over 8. So I'm just going to copy this as a table. It's going to be 1 over 8 here. So 3 over 8, 3 over 8, 1 over 8. So if you sum, so the summation is equal to the 1, by the way. Okay? It's the proper mass function. Okay? So we need to find the variance. So so let's find the variance, and we're going to find this using our new formula which we derived. Okay? So we're going to fill this table. And I'm going to do this by myself because it is easier than before. Okay? So we first of all are going to multiply the x to the p of x. So in this case it's going to be 0, 3 over 8, 6 over 8, 3 over 8. If you sum all of these numbers, it's going to be equal to the 12 over 8. By the way, this is the expected value, right? Or the mu. So in order to get the mu, you just need to multiply x to the p of x and then sum them. It's going to be 12 over 8. So now I'm going to calculate x in a square, which is super easy. You just get all of these values and square them and copy to here. It is going to be 0, 1, 4, and 9. And then we're going to multiply each of these numbers to the p of x. It is going to be 0, 1 times the 3 over 8 is 3 over 8, 12 over 8, 9 over 8. If you sum, what you get is 24 over 8, or simply 3, which is the expected value of the x in the square. So now we know the 2 ingredients of this formula to calculate the variance. It is essentially the 3 minus 1.5 in the square, which is the expected value here. And if you calculate this, it is going to be 0.75. You see, it is much more easier to calculate the variance using this formula. So all the time, just making this kind of table will help you to make all of your calculations neatly, okay, and reduce the probability of making some mistakes. So when I say here that the expected value is equal to the 1.5, it means that if you do this experiment, so make the experiment once, you've got, for example, 2 heads. If you do the second time the experiment, you might get 1 heads. If you do this many experiments, like in millions of experiments, in average you're going to get 1.5 heads in every trial, in every experiment. This is what does it mean, the expected value. Okay? And we can know this before you do those experiments. Before you start doing like 100 experiments, I can tell you, hey, you're going to get 1.5 heads in average. And the variance is difficult to explain 0.75, okay? So we rather use the variance in order to compare the 2 data sets or 2 variables. So for example, if you've got another variable with a similar values, and if the variance is higher or smaller than this value, then you can tell about the spread of the numbers, okay? So the variance, it is difficult to use in order to describe the set or the variable itself, as we can do with the expected value. The variance is better used in order to compare the 2 variables. So this is how we can calculate the variance, and this is what is an expected value. Oh, let's calculate the variance of the ax plus b. It is very interesting because we know the behavior of the expected value of the E when we apply this to this kind of function. The expected value of the ax plus b is equal to a times this expected value plus simply the b. So I would like to know the behavior of the variance. So what is the variance of ax plus b? So let's try to do this together. So you can, for example, guess. So can you tell me why the expected value of a constant is a constant? Okay, I'm going to rephrase this question. I'm going to ask you, why the average of many constant values is a constant? It's obvious, right? If you get lots of values which are the same, for example, 2, 2, 2, 2, 2, 2, 2, right? So when I look to this A as a constant, you need to look to this as a data set with lots of values which are the same. Obviously, the average is going to be the same, 2, right? So that is why the expected value of a constant is a constant. What do you think? What is the variance of a constant?
0.
Huh? 0, right? So because you've got many 2's, 2, 2, 2, 2, 2, and if you find the average distance from a mean, it's going to be simply 0, okay? So so I can tell you, I can preview here that if you apply the variance as a constant, it's going to be 0. But I would like to try to understand the behavior of the ax when we apply the variance, okay? So I think in order to do this, we need to use the formula. So if you know that the variance of the x is equal to the expected value of the x squared minus the expected value of the x, then what is the variance of the ax plus b? So you're going to plug this ax plus b into here. So I need to calculate the expected value of the ax plus b first of all, in the square, sorry. So it is going to be equal to the summation of a square x square plus 2abx plus b in the square. Or I don't need to make the summation. I know how to apply the expected value. Okay, so let me put this like an expected value. So you can apply the expected value to each of these terms. So if you apply this for the first term, it's going to be a in the square times the e of x squared. If you apply this for the second, it is going to be equal to plus 2ab times the e of x. And if you apply this for the last one, it's going to be simply b in the square. Okay? And I'm just going to put this into this formula. So the variance of the ax plus b is equal to the expected value of the ax plus b in the square minus the expected value of the ax plus b squared. So this is equal to a squared e of x squared plus 2ab e of x plus the b squared minus, so I know that this is the expected value of the ax plus b. I'm just going to square this. It is going to be equal to the a squared e of x in the square minus 2ab e of x minus the b squared. Oh well, is it 0? Because all of the terms are the same, right? I mean, I can cancel b squared with this b squared. 2ab was this one. It's 0. No.
Expected value of x squared in the square brackets.
Oh, yeah. These terms are different, right? This term is different from this, right? Okay, cool. So many terms are going to be cancelled. So this term with this one, with this one and with this one. And what we'll have here is a squared, if I take out the a squared from the brackets, it's going to be e of x squared minus e of x squared. They are different, right? Okay, so this is going to be equal to the a squared times the variance of the x. Yeah, so I announced you in the beginning, I explained you this, hey, like if you apply the variance as a constant, it is simply 0. So applying the expected value for this kind of function, linear function, or the variance, it helps us to understand the behavior of these two functions. Okay, so you need to look to this variance or the e of x as an operator. Okay, so it is making some operation over your array. And now it helps us to understand this. So hey, if you apply the expected value to the constant, it's going to be simply constant. And if you apply the expected the variance to the constant, it's going to be equal to the 0. And it's clear, right? Because if you get lots of values which are equal, then the variance is obviously equal to the 0. Okay? So let's finish the lecture today here. So thank you very much for your attention. Bye.